Okay, hello everyone. Thank you for joining us today. My name is Matt Prilliman. I am a researcher and software developer on the System Advisor Model team here at the National Renewable Energy Laboratory. And today, on behalf of myself and the rest of our SAM team, I'm going to be giving a webinar on modeling PV uncertainty in SAM. This is the first in the series of webinars that we're giving this year on topics that have been highly requested from our SAM users and have often been discussed at industry conferences that SAM has attended. So for those of you that maybe had some discussion on PV uncertainty at the PV Performance Modeling Collaborative Workshop in May, we thank you for joining us today. And in the following August, we'll have webinars on modeling financial incentives in SAM and modeling hybrid power systems. Those are also highly discussed topics. All webinars will start at the same time that we're starting here today. You can register for those on the SAM events page at the link below. And the webinar recordings will be posted on the SAM website and the SAM YouTube channel following the end of the broadcast. And those links are available on the SAM website. A little bit of housekeeping for GoToWebinar. We'll be managing questions through the questions pane, either from your GoToWebinar desktop application or on the web viewer. You can type a question in that questions box, and a member of the SAM team, we have the whole team here today, they will either answer your question in chat or flag that question to be answered live on the broadcast. So quick agenda for today. I'll give a quick intro into SAM for those that may be unfamiliar with System Advisor Model, and then go over some of the details of the PV uncertainty modeling in SAM and some of the new features that we added in a project with Sandia National Labs funded by CEDO. Then we'll actually go into SAM for a live demo, and we'll save plenty of time at the end for Q&A. So for those that aren't familiar, System Advisor Model and PVWatts are free open source software that enable detailed performance and financial analysis for renewable energy systems. We're going to be focused on the SAM desktop tool today. That's the primary way through which people access the SAM code, but lots of ways to access SAM, and you can find out more at the SAM website there, sam.nrel.gov. SAM has a very large user base, and you can kind of tell that by the large audience that we have here today. Around the world, SAM is started once every 1.4 minutes. The PVWatts web API receives over 17.5 million hits per month. We have a very international audience, over 200,000 users in over 190 countries. Some statistics there on our views for the webinars like this one, and plenty of external collaborators such as in industry such as Sunrun, Enphase, Southern Company, and more. You can see our Google Scholar citations of SAM grow year over year, and a largely US-based audience, but over half of our users are international outside of the US as well. So thank you all for using SAM and for being here today. Just quick funding acknowledgements and some information about the tools we'll be talking about today. So these features were developed and input into SAM as part of a project with Sandia National Labs, as I mentioned previously. That work was funded by DOE's Solar Energy Technologies Office, CEDO. This work happened between the years 2021 and 2023, and these features have been available from SAM version 2022.11.21 onward. So became first available in 2022 and are still available as of today, the 2023 version. So we're talking about uncertainty and uncertainty in the form of probability of exceedance. So when we talk about like a P90 value, that is the 10th percentile distribution of a future annual energy, or like what the plant is expected to exceed in annual energy yield 90% of the time. That number could be for any value. For example, a P50 would be the 50th percentile of distribution, or your best guess kind of average annual energy yield, or it could be P10, P75, any of those values, just that percentile of the distribution of future annual energy yield. We're focused on the uncertainty tools developed for the PV models, particularly the detailed PV model and PVWatts, which account for the both the variability in weather and the lack of knowledge of future weather, in addition to model and parameter uncertainty. There are some uncertainty tools in other SAM renewable technologies, such as wind and other technologies, but those only calculate P50 and P90 based on the variability in the weather. Whereas the PV has uncertainty, as I mentioned, due to the weather variability year to year, the lack of knowledge of future weather, modeler skill, and the model and parameter uncertainty. The big part of this project was to separate the uncertainty in PV yield estimates into two different categories. Aleatory, which is defined as uncertainty that cannot be reduced with improved measurements or models. An example of this is future energy that cannot fully be known. And the epistemic uncertainty, which is the uncertainty that we can reduce with more accuracy, better measurements, improved models, that kind of thing. And the example I have here is for temperature coefficients. So the key thing of this uncertainty feature is to look at the aleatory and epistemic uncertainties separately and combined to get a better understanding of what we can improve in our uncertainties and where the main uncertainty in the annual energy yield lies. The steps in this process in this uncertainty tool, we have factors on models or parameters for uncertainty. You can define those factors as distributions on the annual energy yields, or uncertainty and the effect of those factors on the annual energy yields. Calculate that base annual energy for each weather year. We need minimum 10 weather years. Apply those base annual energies to 1,000 randomly sampled factor products. So a combination of all those model factors and the epistemic combined with the aleatory to then analyze the individual components of the uncertainty in addition to their combined annual energy yield distributions. And this leads to a very robust number of weather years times 1,000 factor sample size with 12 different epistemic factor categories included in SAM to vary for their uncertainty effect on annual energy yields. We have a screen cap of those different epistemic categories here for the different model or measurement categories and those effects on annual energy. You can define those through different types of distributions. And a new upcoming feature in the latest patch that will be coming out in the coming weeks, you can turn on or off individual categories with a checkbox to exclude those from the calculations. As I mentioned, those distributions can be modeled as any type of uncertainty distribution. And in those interfaces to do that, we have helpful images explaining how those distributions work and what the variance is and how to define those. From the uncertainty tool in SAM, which we'll get to in the demo in a second, you can import your own weather files. You need a minimum of 10 years of weather data to run these uncertainty calculations. Or you can, from the National Solar Radiation Database, an NREL product, you can download all the available years of weather that the NSRDB has for that site. And you can also modify which probability of exceedance value to model, whether it's a P90, P50, or what you want to look at in your results. And finally, when you analyze your results, you can look at the combined aleatory only and epistemic only uncertainty results through different graphs, and then you can export the data and look at it that way. So we'll get to that more in the live demo. So those are the slides. I will pause to let Janine or Paul let me know if there's any show-stopping questions to get to before we move over to Sam.
None at this point. Go ahead and proceed.
Okay. So when you open SAM, this will be the front page that you'll see. I will start a new project. And under photovoltaic, you will have the option for detailed PV model and PVWatts. I will do the detailed PV model in this case. And for this example, I will use an LCOE calculator model just with a simplified financial structure. The uncertainty modeling that we'll go over won't have any impact on your financial analysis within SAM. It can't be used externally, though. So that will load in and you'll see a variety of different model categories here that'll be important for defining some of our factors. And then to look at the specific uncertainty tool, you'll notice under the simulate button, we have this uncertainty button. We'll click that and that will take us to our interface for the uncertainty tool. So I'll actually switch over to a different tab where I have one already started. Here we have some things already run, but I'll kind of go through how all this works. Here you can see we have our 12 different categories. We have irradiance transposition, horizon shading, row shading, the module rating at the standard temperature conditions, the standard test conditions, inverter availability, spectral response modeling, cell temperature modeling, mismatch losses, DC wiring, transformer losses, and soiling losses. And each of these represents the uncertainty from that modeling factor and its impact on the annual energy yield. So the important thing for quantifying these categories is that each one must represent the effect of this component on the annual energy yield. And so it must be defined as a percentage on annual energy with if it's normal distribution, a mean and a standard deviation of variation on the annual energy yield and the percentage. So if I wanted to change one of these distributions, I would go to this edit button on the side here. I would choose from my different distribution types, whether it's normal or triangular or others. And I would specify the relevant variables and then click OK to set that change. Each one kind of has a helpful descriptive text on these icons on the left to kind of give you a better idea of what's accounted for in these categories. And you'll notice that some of these, like the irradiance transposition, spectral response, and cell temperature are 0. And when I initially got this page, the boxes were unchecked. And that is because in our default SAM modeling, we are accounting for these models. We are running transposition models in our base calculations. We are accounting for a spectral response in the base case simulations. And we are modeling cell temperature in those simulations. So as not to double count those, I was unchecking these boxes. This is an example of kind of decisions you can make in quantifying these cases. Other categories were not by default modeling in this case, or a good example would be maybe if you're modeling, instead of using GHI or DNI in diffuse irradiance and using a transposition model, maybe you're using measured POA. You might want to change this to account for the measurement uncertainty and how you got to that POA. Plane of array irradiance in your model. Once we have these defined, you can look at your weather folder. You can choose a folder that has only the relevant weather for your system. So I have an example folder here with all the weather for Golden, Colorado. Or you can click this download from NHRDB down here, and you can search by your latitude and longitude for what weather data is available from the NHRDB for your system. And you can download all those into a folder from this interface. You can, as I mentioned in the slides, calculate P90 or change this value. So when I finally have all this set up, I will click Run Uncertainty Simulations here. It's important to run this one. And this Simulate button is for the base case simulation, whereas this is running our uncertainty calculations. So I'll click Run there. I'll note that while this is running for these types of cases, if you're running this initial case, it'll run faster without a detailed financial model attached to the PV. So that's why I ran a LCOE calculator case for this example. You could also run it without financial model. And then we can see results loaded down here. We have graphs for the overall uncertainty, which is the combined epistemic and aleatory results, only the results due to the interannual variability and or the aleatory, and then the results from the epistemic uncertainty factors and that combined factor product P90 value. Each of these graphs has different bins with a percentage of data points within those bins on the left y-axis, and on the y-axis they have a cumulative distribution function of all the different data points. You can change the number of bins based on a calculation or by a set fixed number of bins. You can change them to a histogram versus a scaled histogram for the combined. Kind of neat user interface trick here. You can drag in the bottom right-hand corner here to make these bigger. And then if you right-click any of these graphs, you can, a lot of options for data export. You can copy the data, send it to a CSV or Excel. You can copy the image and save it to the clipboard, or you can export the image as a PDF as well. And you can do that for all of these graphs. And to show if I want to change my p-value, I want to look at a p50 instead of a p90, I can change that and then click change p-value. And that will move where these blue lines are on these plots, which are where on the cumulative distribution function that p50 or p90 or whichever value you choose, where they lie in each of these uncertainty categories. So that's a high-level look at how to use this tool. I'm sure with some questions we can get into more detail on certain aspects of it. So do we want to move to questions?
Yes, we have a few that we can prep you with at this point. The first question is, how do you determine the distributions for each of the uncertainty parameters?
Yeah, so that's kind of the big question left with this work is, how do you decide on the factors for each of these? There has been some work done by, I know there's the IEA task 13 report that looked at some of this, that kind of has some values that we looked at for kind of defaults, but a lot of this just comes from data. I know Cliff Hansen from Sandia had a good paper at the 2022 PVSC about kind of quantifying uncertainty for ground irradiance measurements, and maybe an approach similar to that, to the work he did, could help with kind of quantifying some of these. But for some of these, we don't have great guidance yet on how to quantify what they should be, what you should use for these inputs, rather than if you have a lot of field data you can access and use.
Thank you, Matt. We have someone wondering if you could elaborate a little bit more on the difference between just pressing the simulate button within the base case and a P50.
Yeah, absolutely. So everything in this gray box here, this all represents our base case. So I kind of skipped over that, getting to the uncertainty tool, but we have our base case PV simulation with one weather file selected. We have our module defined, our inverter, our system, and all our losses. And then if we click simulate on this base case, that will get you one annual energy result and basically one calculation. And then if we go to the uncertainty, this is looking at, let's say, 20 years of weather data in this example, times 1,000 samples, and that's getting you 20,000 estimates of annual energy. And looking at, the uncertainty based on these factors, based on the different weather data, and looking at that. So this has a lot more data, but this is only looking at annual energy, whereas when I click the base case simulate here, and then you can look at the results from that case with this little button to the right of it. You have more granular information on losses for that base case simulation and financial results if you're running your financial model here as well.
Great.
So this uncertainty tool basically it was built to focus on looking at the uncertainty in the annual energy and look at those different probability of exceedance values for that annual energy yield.
Fantastic. We have a few clarifying questions, so we'll go in what I hope is a logical order. One is asking if you could provide a little bit more detail on how to interpret these figures that you're showing on the screen here.
Sure. So I'll use the combined uncertainty as a starting point. On this graph, we have two y-axes. This left axis is the percentage of data points. This corresponds to these different bins, these different columns here, where each bin has a percentage of data points that the overall energy yield falls between those values. So it's kind of counting where does your annual energy yield lie as a percentage of the data points within these evenly spaced bins across the range. And then the right y-axis is the cumulative distribution function, which is counting all of the results, the simulations, and looking at what is counting up to all the results and where does each energy prediction yield lie. So we have our P50 is kind of falling right in the middle of that distribution function. So that's kind of where that 50% mark is. If I changed it to 90, then that would be our P90 or our 10th percentile of that future energy yield. So that's kind of where that blue line lies in my graph. And if I export this, maybe it'd be a little bit clearer looking at it in Excel. We see our data points of kind of where how many percentage of our data points do not exceed this overall uncertainty in these different bins and these first two columns. And then in the right-hand column, it's counting all of our 20,000 simulations and counting up to going from 0% of our data points to 100, just counting up, kind of listing them in rank order of where they fall and where our P50 falls, basically. So I hope that cleared things up a little bit. There's similar, let me go into more detail on the other two. Similar things for the other two graphs. This is based on our weather data. So it's picking the weather year that has the P90 or the 10th percentile result for that, just based on the variability in weather data. So that's this blue bar here. If I change it to P50, it'll pick our P50 weather year instead. And this bottom graph is just based on the combination of the factors or the fraction of annual energy based on these. So these factors in annual energy are percent in annual energy. So it's kind of a 1 minus, if this is 1 minus, let's say this were 2%. 1 minus 2%, then that would be a 0.98 average. And then with the standard deviation, either in positive or negative direction, it would randomly sample that 1,000 times, and it would multiply that by the samples of each of the rest of these factors, and then running this, it'll have the same kind of binning of that final fraction based on all the factor products and the same percentage of data points and the different bins, and then the cumulative distribution function that finds the P50 of just that factor that gets applied to the base case from the weather year.
Thanks, Matt. And we have gotten a variety of questions to the effect of asking if this feature is available at all through PySAM or our API from different programming languages.
So not currently. Currently, this is only accessible through the user interface, but the methodology is just a kind of a basic Latin hypercube sampling method for the factors, and so that is something that maybe we could explore more in the future, making that accessible through different things. But the methodologies are in the report, which is linked. I think we'll share the slides after this. Linked in the slides, that methodology, and so it could be the same method could be used in Python, but it's not something that we have through PySAM or through our API right now. But maybe that's something we could explore more in the future.
Thank you. And to build on that a little bit, there's a question of whether or not this uncertainty simulation feeds into the base case analysis at all, or is it a standalone sort of add-on feature? And related, whether or not then you could use it in conjunction with the financial model.
Yeah, so trying to think of how that would work. Currently, there's no like built-in like take this P50 and then run financial analysis based on that P50 results. Maybe that's something that we could investigate more in the future in the user interface. Likely that's something you could do in PySAM if you know your annual energy yield as a result. You can do some financial analysis on that and use the financial models in PySAM or in a user interface to kind of look at that. But we'd have to think a little bit more about how to make that a built-in feature of the user interface. So.
Thank you, Matt. And I'll add in that we do track user feature requests and wish list items on our GitHub repository, which we can link in the chat. Our ability to make improvements to the model is dependent on funding. So we do sometimes propose some of the features that users have requested to try to get funding to implement them. We also do work directly with private companies sometimes, and our code is open source. We love open source contributions for new features as well. So just a quick plug on some of that. And then Matt, we have a clarifying question about whether this is a Monte Carlo simulation. Can you clarify a little bit on the methodology for the uncertainty piece, sampling and whatnot?
Yes. So the sampling of the factors is a Latin hypercube sampling method. So that's how we get our random results from that. So no, it's not a Monte Carlo. It's a Latin hypercube sampling. Unless Steve can chime in if I'm misremembering any of those details.
We have a question on the screen that you're showing right now where it says number of bins Friedman-Diaconis formula, which I hope I pronounced correctly. Can you talk more about that dropdown?
I can a little bit. I don't remember the exact Friedman-Diaconis formula. I think you can find that Googling it. I think it's just different options for how to specify how many bins. This is kind of more of a formulaic approach based on the data itself, whereas you can also just say, well, I want 20 bins regardless of what the data looks like, or I want 50 or I want 100. So that's kind of the option there for these two graphs. And then for the weather year variability graph, it's just one bar for each year of weather data.
Thanks, Matt. There are a few questions that I'll cover for you to give you a little bit of break on talking, because I know you've been talking for a bit now. There's one asking that says the uncertainty tools seem to be available for detailed PV, but not the PV battery. Instead, the button says P50, P90. What is the difference, and will uncertainty be available for PV battery? So I'll go ahead and take that one. The button in the other models that says P50 and P90 was our previous iteration of a first step an uncertainty analysis, and Matt is going to go ahead and pull up that user interface right now. Thank you, Matt. That user interface deals just with the weather uncertainty, so it's basically the same as what Matt was showing for selecting a folder of weather files that you want to run the simulation with, and then sorting those into how much variation in annual energy you get. The reason that we don't have this detailed uncertainty feature for all of the other technologies really boils down to a lack of data to provide some of those categories for the sources of uncertainty that you define with distributions, as well as some lack of data on what those distributions should be as defaults. However, we would love to expand this feature to other models, and we're hopeful that we would be able to get some funding to do that in the future. And again, if folks are interested in those types of features, please do chime in either via email in the chat now or on our GitHub repository where we check user feature requests. I will go back to Matt with the next question, which is a little bit related. It asks if clipping losses are quantified elsewhere in the model since they don't appear in this list. Since it looks like we didn't prep Matt on having the appropriate weather files for doing the P50, P90 on a PV battery system at the moment. You want to talk about the clipping losses, Matt?
Yeah. Yeah, so we don't call that out explicitly in the uncertainty factors. We have added in the last release, we have added inverter clipping modeling. So because that modeling is accounted for in that base case, if you turn that model on it's on the losses page actually. If you turn that model on in your base case, and then when you go back to run your uncertainty simulations, that inverter clipping model will run in all of these cases, and then you wouldn't want to put a factor here to have to double count in that. So the inverter clipping would be reflected in your results. It just it's not an explicit factor here. And like for an example, we don't have an explicit inverter availability modeling in the base case, so we do have that factor here for uncertainty and annual energy due to inverter availability. So yeah, that's kind of that's how it works for a lot of these models. If you turn on the model option in the base case, it will be run in all of the subsequent uncertainty calculations. So if you, for example, turned on the self-shading model and you went back to the uncertainty, you might want to take out the row-to-row shading uncertainty in here because you don't want to double count for that in your results. Hopefully that clarified a little bit.
Thanks, Matt. There's a question about, is the uncertainty feature always on an annual basis? And if so, is there any work on shorter timescales?
Yeah, so at the moment, yes, it's only looking at annual energy. That'd be another thing, like Janine mentioned, future requests to look at other timescales or monthly energy or that kind of thing. To expand that capabilities would be kind of a new feature. And dependent on funding and user interest. So we definitely like to hear what other timescales people are wanting to know, wanting to do this kind of uncertainty analysis on.
Thanks. And there's a couple questions asking for a little bit of clarification of what you mean by double counting the uncertainty for something, which maybe I can tackle again to give you a little bit of break on questions. So when Matt is saying that, for example, the irradiance transposition, we do model the transposition specifically, and so you may want to disable that uncertainty category. There are some sources in the literature that don't disaggregate the effect of the irradiance transposition model from the uncertainty in that model. And so if you are looking at a reference like that, it would be double counting to use that value. For example, it might say it's something like 10 or 14%. I believe that was in one of the IEA reports. Then you would be double counting the effect of the irradiance transposition model. So you could still leave that source of uncertainty checked on the uncertainty page. It just you need to make sure that the magnitude of the error you're putting in represents only the effect of that uncertainty on the annual energy and not the effect of the model itself. So if you believe that the uncertainty in, for example, your cell temperature model or your irradiance transposition model is sufficiently small that you want to ignore it, you might uncheck some of those boxes. Hopefully that helps clarify what Matt is talking about when he's talking about double counting the sources of uncertainty. We're really just making sure that you want to not include any effect of the model itself when you're assigning these values in this user interface. Anything you want to add to that, Matt?
No, I think that was, yeah, a very good clarification, because, yeah, this stuff can get pretty convoluted pretty quickly with the modeling and the factors. And yeah, so thank you for that.
Absolutely. There's also a question about whether or not this could be used to run a sensitivity analysis. Could you please demo the sensitivity macro quickly? Because it is a slightly different feature that we do have available in SAM that the uncertainty feature might not be the best way to do.
When you say the sensitivity macro, you're referring to this one?
Yep, thank you.
Okay, yeah, so this is a different tool under macros, which is right next to the uncertainty button. Macros are scripts that are included with SAM to kind of extend your base case analysis in a similar way to uncertainty, but just kind of smaller pieces. So we can make tornado charts with sensitivities of various parameters. You can select input parameters on the right here. So what if I want to say tilt for subarray 1? And I want to look at annual energy. Sorry, I haven't used this in a while, but you can do oh.
It's not a live demo if something doesn't work like you want it to.
Right. Okay, this isn't working right because the tilt is at 0. So let's change that and try again. So yeah, there's a very basic example of the kind of outputs that we get from this macro for a sensitivity analysis. There's also, you can vary inputs parametrically through this parametrics tool and do things that way as well. So you can look at some sensitivities that way. So yeah, lots of different features here.
Yes.
Go ahead.
Sorry, Matt. We also have some videos on the SAM website that demonstrate some of these other features as well. So please check out the SAM website, sam.nrel.gov. And along the left, there are some tabs and some videos where you can find how-tos on some of these other features. Thanks, Matt. We do have a question going back to the uncertainty feature. Someone asked if the uncertainty feature is turned on by default. So I think it's worth emphasizing that just clicking simulate does not run these uncertainty calculations. That runs just the base case scenario that you have set up in SAM. In order to access these features, you have to go to the uncertainty box that Matt is hovering over right now and set these inputs separately and click the Run Uncertainty Simulations button at the top. That will allow you to run this feature. So it's sort of an add-on to the normal base case simulation. We have a question here that I'm hoping I know Paul is busily typing answers to other people's questions, but I think this one is perhaps worth, Paul, if you're available, a live answer to, which is whether we can use the uncertainty module to determine uncertainty in string voltage for design. And I think that this usually pertains to the NEC code that people are using for string voltages. Paul, are you able to talk a little bit about what we have seen some other users, how we've seen other people use SAM for that kind of design?
Yes, and this is related to a couple of other questions about how to use the results of this uncertainty analysis for, financial modeling and so on. And I think the basic answer is that you would run, so this uncertainty analysis that we're looking at here is based on the annual energy. So you're looking for, you use the uncertainty analysis to identify the weather file that represents a desired p-value. So if you're looking for p50 value, for example, you'd run the uncertainty analysis and then you'd use the graphs to find out which year represents the p50 year. So that whatever year represents p50 means that the annual energy that results from the simulation for that year is equivalent to the p50 annual energy value. So then you could use that weather file in a base case simulation and look at your hourly results. So if you're focusing on, if you're looking at what the probability of the open circuit voltage exceeding some value is, you could base that on the P50 weather year, and then know that your open circuit voltage analysis is based on a P50 weather file, and that would be the same for other analysis. If you're looking at different modules and inverters and so on, you can go back and forth between the uncertainty simulations and the base case simulation.
Thank you, Paul. We have gotten a couple of questions also about using the uncertainty feature for hybrid systems or battery systems. As we mentioned, this uncertainty feature is currently only available for the PV model. However, you could use some of your information about how the uncertainty in the PV system looks for your system to help size a battery separately. It would be a bit of a manual workflow where you'd have to evaluate the uncertainty in the PV system and then separately choose how you want to apply that to sizing either a hybrid or a battery system. I do also want to point out that we have an upcoming webinar specifically on modeling hybrid systems in SAM in a couple of weeks on Tuesday, August 27th. So if you are interested in hybrid modeling, please do sign up for that webinar and join us, where we will be happy to answer hybrid questions there. There's also another question that I think is worth reiterating verbally for everyone, which is someone asking what version of SAM Matt is using, since they don't see the checkbox in their version. Matt, would you like to clarify that?
Yeah, sorry for the confusion. So I am working off a development version of the most recent release. So you currently, if you open SAM, you will not see these checkboxes. And if you want to zero out these values in the meantime, the thing to do would be to use a normal distribution with a mean of 0 and a very small but non-zero standard deviation, and that should work that way. But these changes and these updates to some of the default values and the addition of these checkboxes will be coming out in revision 2 of this version of SAM, which will be coming out in hopefully the next week or so. So be on the lookout for that very soon.
Thank you, Matt. So for any future folks watching the recording of this, likely the version of SAM that you have will have these checkboxes in it. There were a few questions on the graphs that this produces and different ways to export those graphs. Matt, could you quickly demo this feature, which we have available on most of the graphs in SAM, being able to right-click them?
Right. So yeah, I generated these graphs here. I right-click and lots of different options to copy the data that it was used to make the graph. So I showed you earlier tabular results from those graphs. You can export that to CSV or to an Excel file. Excel, yeah. You can save the image to clipboard as image file, or copy it to clipboard and then or export as an image. So if I do that, it'll save it as a file. You can save it as a PNG, JPEG, or BMP file and save that to your files.
Thank you.
Or I'll export as a PDF and do the same thing, but in PDF format. So lots of export options for images, for reports, or for the raw data used to make these graphs so that you can then take that into your own analysis.
Fantastic. Thanks, Matt. We got a few questions asking about what module or inverter or system tilt or things like that these simulations were using. I think probably from people who joined late, so it's worth emphasizing that anything not specified in the actual uncertainty page is using the value that you specified in your base case simulation here. So we expect that you would go through and set up your actual system with the correct module, inverter, string length, etc., prior to running your uncertainty analysis, where you would then add on the uncertainty categories that you would like to analyze. And we do have separate videos on the SAM website about setting up PV systems at various scales. So we encourage you to check those out if you need a bit of a primer on how to set up your base case simulation in SAM. There was also a question about probabilistic modeling, and I think it's worth differentiating a little bit. This uncertainty capability is basically using two different ways to combine, as Matt mentioned, the epistemic and aleatory sources of uncertainty. And the reason that we are running it in this particular way is for speed. So we do have a stochastic feature that you can see underneath the simulate box as well. That allows you to select any input variable and assign a uncertainty distribution to it. You can add correlations, and then you can look at the effect of that uncertainty on your outputs. And you can add a weather file folder to that feature, much as you can in the uncertainty feature. However, if you wanted to analyze 10 or more different inputs for uncertainty, this starts to get very slow doing it the way that this feature is set up. This one is more of a true Monte Carlo analysis, running, you know, X number of simulation or samples that you specified. And so the uncertainty feature is really a slightly different approach to that, that is faster and more able to combine the epistemic and aleatory sources of uncertainty slightly differently, and then it has the embedded graphing capabilities. So for PV simulations, we do think that the uncertainty approach to doing it is a little bit more tractable for many people modeling systems. Do you have anything you would want to add to that, Matt?
No, I think you covered it well.
I'm reading through, we still have some questions, but many of them have been answered. There's a question asking a little bit more, I think, of an introduction of how the probability of exceedance is used. So that P90 or PXX value that you were talking about. Do you want to take that, Matt, or would you like me to?
Yeah, I'll take it. I could just say that generally these values are used like in yield assessments or yield predictions. This P50 is typically taken as like your best guess or your yield that you expected to be exceeded. You expect your system to outperform this estimate 50% of the time, whereas for a P90 you would expect it to exceed 90% of the time, that kind of thing. So a system underperforming a P90 value would indicate that there's either something wrong with your estimate or your model estimate, or there's an issue with your system. So it's kind of used to evaluate that and look at risk and investment and that kind of thing. So that's generally how they're used in the real world.
Yep. Yeah, frequently the financier is the one who cares most about the P90 or whichever metric they choose value. The questions are starting to slow a little bit, although I see we still have a lot of people online. So thanks everyone for sticking around. And while I wait to see if there are any final questions for us to address live, we'll remind you that we will be posting the recording of this webinar to the SAM website, and we do generally post a transcript of the Q&A as well. So you'll be able to take a look at any questions that we answered in the chat instead of live by voice as well. And there's a question of if the slide deck will be shared. You know, I can't remember if we typically, I think we typically share a PDF of the slides.
Yes,
yeah,
we'll
it'll either
share.
be. Go ahead, Paul.
We'll be posting a link to the recording, a PDF copy of the slides, and a transcript of the Q&A session, and that'll all be on the simulation options page on the SAM website. The simulation options page is where we describe the PV uncertainty feature.
There are two last minute questions coming in about the values for the distributions. One is asking if we can link the report that we used for the distributions that we mentioned. So that has been put in the chat. And again, we'll post a transcript of the chat so folks can get access to that as well. And the other question is, if NREL isn't providing guidance on how you should adjust the uncertainty parameters, how confident should users be in utilizing the default uncertainty values and distributions? And I'll say that with many things in PV modeling, the biggest problem for folks trying to run models is frequently lack of data, and NREL doesn't necessarily have all the different kinds of data that we wish we had for determining better values for some of these uncertainty distributions. So we have put in default values that are consistent with the best data we have access to. Folks like system operators or independent engineers probably have access to more plentiful data that may allow them to more accurately assign uncertainty distributions based on location or panel type, things like that, that unfortunately we don't have access to, which is a good plug for sharing some operational data that can be used to improve everyone's estimates of uncertainty. The Department of Energy has prizes related to that, and it's sort of a frequent ask for by folks at NREL and other national labs, because sharing data is in everyone's best interest. So if you are in a position to share some of that data, we encourage you to do so. If you are in a position where you need that data and don't have it, we're sort of in the same boat. So we have provided default distributions to the best of our ability, but they may not be perfectly representative. So they're better than nothing and maybe not amazing for your particular system. We'll see if there's any last minute questions that come up, but we do have only 2 minutes left. I don't know, Matt, if you had some wrap up slides or anything to say to wind down.
No, I was just going to say, yeah, thanks everybody for your time and your attention today. I'll just close with the schedule for August. We have 2 more webinars that'll be just as informative as this one, if not more so. So please be sure to tune in, especially there was a lot of interest in hybrid systems. We'll have a lot to talk about on that one on the 27th, and modeling things like the ITC and PTC on August 13th. So be sure to tune into those.
Excellent. Thank you, Matt. There are a lot of questions rolling in saying thank you for a wonderful presentation. So we'll make sure to pass that along live.
Yeah, thanks everyone.
All right, thank you everyone. And with that, we'll go ahead and shut down. Have a great rest of your day, and goodbye.